So we wrapped up last time we were doing the shell method, and we had started this question. And let's go through it slowly and catch up to where we were. So the idea is that we are trying to find a geometric shape that you can imagine replicating a bunch of times to fill out the entire solid object. And the shapes that we've used so far had primarily been disks and then washers and now shells. So you could probably come up with other ones. So we're imagining filling out this solid object with all of these cylindrical shells. And we need to find the area of that shell. And integrating that area is going to find volume. So once again, we have our three quantities. We have distance, area, and volume. If you integrate distance, you get area. If you integrate area, you get volume. So that's our basic sort of base understanding, foundational concept. And so when we look at our generating region here, we need to choose an element, an integration element. So that's what the red line is. That's our integration element. You can imagine it as a little rectangle. And when that little rectangle rotates around the x-axis, it's creating this red cylinder. Okay, so when we're doing shells, the element that we choose is parallel to the axis of rotation to create that cylinder. And remember that when we do disks and washers, that element is perpendicular to the axis of rotation to create a disk, or to create a washer if there's a gap between the element and the axis of rotation. So we've got our cylinder. And we all know the area of a cylinder. The area of a cylinder is the circumference, 2 pi r, multiplied by the height. 2 pi r h will give us the area of our general cylinder. So the one thing that's more complicated with shells or cylinders is that you have distances that are both parallel and perpendicular to the axis of rotation. With disks and washers, everything is perpendicular to the axis of rotation. But for a cylinder, we have both. There's our axis of rotation down there. The radius is perpendicular to the axis, and the height of the cylinder is parallel to the axis. So that's why it's a little more complicated, because we have both going on. All right?
Will the radius always be wire x?
It'll always be wire x unless we're rotating around a non-axis, a non-coordinate axis. So if we pick a random axis, then x and y might not be the radius anymore. But it'll be related to x and y. It'll just be shifted. So if you're going around a coordinate axis, yes. So when we look at this element, anytime we draw a horizontal element, we think of it as at a random y. And that y is, in fact, measuring that distance down to the x-axis, which is why it is the radius, right? Really? That distance right there is y. So that distance is corresponding to exactly how far away from the axis of rotation that horizontal element is, which means it's the radius. Y is the radius. Another case that could happen, if your region happened to be below the below the x-axis, and you were rotating around the x-axis, then your r might not be y, it might be negative y. You know, if your region were down below so that your horizontal element was at a negative y value, then you would say your radius would be negative y. Okay, so here's our setup then. We've got our 2 pi r. We need to replace the r and the h with something that has y's in them. And basic principle again is that the element is perpendicular to the y-axis, which means we're going to be integrating with respect to y. And you sort of think about it, this element is just representative. There's an infinite number of horizontal elements here, right? They're all forming their own cylinders. And so we're integrating in this direction. We're integrating in the y direction. And so that is just a confirmation that these two quantities, r and h, get replaced with expressions that have y's in them. We want to have y's in them because we are going to be integrating with respect to y. So that's just a check. Double check that this letter here matches the integration variable. So we just talked about the radius. The radius is y. Right? That element is y units away from the axis of rotation, which forms the radius of the corresponding cylinder. Height is a little more complicated. The height is a horizontal distance. Anytime we want horizontal distance, we're going to do the right x-coordinate minus the left x-coordinate. Right minus left for horizontal. So we look at our two curves. The curve on the left is just this vertical line. X is already isolated here. X is going to be that 1 over root 3. The right curve, oh, they did isolate x for us. If they gave us this curve written as an isolated y, we would have to rewrite it so that it was an isolated x. So once it's written as an x value, once it's written in the form that measures horizontal, then we do that right x minus the left x. So that'll give us the height of the cylinder. So any questions on that setup, getting to that point where we've used our generic formula for the cylinder and then replaced from our picture? Any piece of that you're not sure about? Okay, so then the let me select home. Interesting. That is not selected. It's weird that it's not letting me scroll. It's letting me scroll every day until now. And that scroll bar, I can't even see the scroll bar over there. Geek. Okay. So let's go ahead and simplify the area of this cylinder a little bit. So the area of the cylinder, we have 2 pi. I'm going to distribute the y to the inside. And so we're going to have 4y divided by y over y plus y cubed, and then minus y over the square root of 3. So there's the area of the cylinder. Area of the cylinder at a height of y. Volume, like we said, is just the integral of this. So we're going to have 2 times pi integral. And I'm going to cancel a y out in this one. So we have that. And then our limits of integration, if we look at our picture, they tell us that we're going from y to root 3 on the y-axis. So they've given us the limits. We're not having to do a simultaneous solve or anything. Oh, now it works. Let's see, 1 to root 3. So we have that as our integral. Okay, so there are a couple of examples that you'll see in your homework in the chapter 6 chapter where you may not immediately recognize the antiderivative. And these tend to be a couple of inverse trig functions. It all depends on kind of how familiar your how much you did in Calc 1. So if we go to the chapter formulas, the inverse trig functions are right here. We're going to do a lot of them in chapter 8 and 9. In this chapter, there's two examples that I can think of where we have to integrate to an inverse trig function. So here they are, though, as a reminder. They're in the chapter formulas for the class. The one that you will see the most is the inverse tangent one. The inverse tangent one you will see, probably several dozen times this semester. And so one thing that you should have in your mind, at least, is a picture of the inverse tangent function. And the inverse tangent function, for most folks, it is the first function that you see that has two horizontal asymptotes. Right, so the inverse tangent looks like that. There's a horizontal asymptote at pi divided by 2 and at negative pi divided by 2. So that is what the inverse tangent function looks like. And it just so happens that the integral of 1 over 1 plus x squared will give you inverse tangent. We'll talk about why that is in chapter 8 and 9. We'll do a bunch of inverse stuff. At this stage, oh, really?
Oh.
Did I log on too fast to the computer? So at this stage, you just sort of have to know the two that you will see in this chapter. There's one that was an inverse sine, and there's this one that's an inverse tangent. So this is going to integrate to inverse tangent right here. So the 4 is a constant, so it will be 4 times the inverse tangent of y. And then this one is a polynomial, so we're going to get y squared divided by 2. There's already a constant in the denominator. It will get combined with the 2. And let's see. I guess that's everything. And that goes from 1 to root 3. So any questions? Yeah?
Will you have to memorize all the chapter formulas?
Yeah, the chapter formulas are the ones you'll need to know. Those are the ones you want to have memorized for each of the exams. So this first exam, if you look up there, the chapter 6 formulas, those are the ones that you're going to need to know. Yeah.
When it comes to the inverse trig functions, can we also write them as arctangent?
Of course, yes. Yeah, definitely. Yeah, in the old days when all we had were typewriters that were really crappy, they would write arctan instead of tan to the minus 1 because they couldn't typeset that easily. So arctan was just an easier thing to write. And there's some other reasons why we sometimes call it arctan versus inverse tan, which we'll see when we get to the inverses. So either one is fine, though. Arctan, inverse tan, it's totally fine. They are equivalent. So let's go ahead and substitute in the upper limit. So we're going to have 4 arctan of root 3. Let's write that out. I won't evaluate that instantly. Hopefully you can. And then we put the root 3 in the second term here. We're going to get root 3 squared, which is 3, divided by 2 root 3. So there is the upper limit. And then we're going to subtract off lower limit evaluation. So we have 4 arctan of 1. 4 times arctan of 1 minus 1 divided by 2 root 3. All right, so there's our substitution of the upper and lower limits of integration. Now we have to evaluate these arctan functions. So what I hope you remember, the way you should be thinking about inverse trig functions and their values, you should be thinking, A, that they are restricted angles. So an arctan, if they're functions, there's never an infinite number of solutions to these types of things. They are functions, but they are restricted. So the arctan function is restricted to either the right or the top half of the unit circle. Does anyone know which one it is? Inverse tan?
Right.
Right half of the unit circle is where the inverse tangent is restricted to. So inverse tan in your mind, it can't be negative pi over 2 or pi over 2 because tangent of those values is undefined. So arctan is always restricted to the right side of the unit circle. So arctan of whatever it is, I'm just going to put a t there. So anytime you see an inverse trig function, you should be thinking angle. That's the first thing. It's an angle that's restricted. So a restricted angle. Arctan is restricted to the right side of the unit circle. Arcsine is restricted to the right side. Arccosine is the one that's on top. Okay, so arctan. And the way you should be reading this is the angle on the right side of the unit circle with a tangent value of square root 3. That's how you should be reading that. Angle on the right with a tangent value of root 3. This angle on the right with a tan value of 1. That's how you should read it. Now, when you're thinking about your tangent values, what is really important, hopefully it's clear, if it's not, hopefully we can make it clear, is that tangent values on the unit circle are slope. Tangent is the slope of the terminal ray. So for example, when we look at, let's look at our standard 12-sector unit circle. When we look at our 12-sector unit circle, these two places right here, this is 1/2 comma square root of 3. The slope of that is going to be root 3 if you simplify. The slope of this one over here, let me move that. Whoops, that's not what I meant to do. Let me move that and put the, let's see, that's not what we want. Let's just move this thing over a little bit. You need to be moved also. So the slope of that one is root 3. The slope of this one is 1 over root 3, which you could write as root 3 over 3. So on the 12-sector circle, those are the two main slopes. You take the y-coordinate divided by the x-coordinate, and that gives you the slope. So here you're taking root 3 divided by 2 divided by 1/2. Right, the y over the x. And in the middle, so on the 8-sector unit circle, the one in the middle, what is the slope there? If you're right in the middle, slope is 1. So those are the three slopes. Root 3 is the steep one at 60 degrees or pi over 3 radians. Slope of 1 at 45 degrees or pi over 4 radians. Slope of root 3 over 3 if you're at the shallow one, the one that's at pi over 6 or 30 degrees. So when we come in here to evaluate then, this is how we're going to do it. So we're going to say, okay, inverse tangent of root 3, that's the angle on the right side of the circle with a tangent value of root 3, that's right there. That's pi over 3. So 4 times pi over 3. Minus this, we rationalize the denominator, multiply top and bottom by root 3. Everyone okay with that? So we're going to get root 3 in both top and bottom, multiply. And so when we do that, we're going to get 3 root 3 divided by 6. And then the 3's cancel, so we'll get root 3 over 2. And we don't need that parenthesis. And then here, arctan of 1, angle on the right with the tan of 1, pi over 4. So pi over 4 times 4. Let's just leave the multiplication for the time being. And then plus, again, let's rationalize here. So we're going to multiply by root 3 over root 3. Distributing the minus gives the plus, so we're going to have root 3. Multiplying the bottom by root 3 is going to give 6. So we have that. All right, and any questions up to that point? And the 4's will cancel here. And then we just have to add all that together. Common denominator of 6 seems pretty straightforward. So So we'll get a common denominator of 6, so it'll be 2 pi multiplied by something over 6. That, we're going to have 8 pi minus, to make that 6, we multiply by 3, so 3 root 3. To make that 6, we multiply by 6, so that's minus 6 pi. That already has a 6, so we're at that stage. So our final answer will have 2 pi multiplied by, looks like 2 pi minus 2 root 3 divided by 6. I guess we're not at the final answer yet. There's still a little more simplification. And divide out the 2. And then I think we are finally simplified. So we've got that. All right, anything about that you want to ask about? Any step there? Yeah.
Is it possible to factor the 2 pi into the numerator?
To distribute it?
Yeah.
Yeah, you could distribute it. Definitely. Yeah, so you could distribute the 2 pi into the numerator if you want. Usually we factor, but it doesn't matter. Aiden?
Would this be an accepted answer on the exam?
Yep. 100%. That would be perfect. Any issues with the evaluation? Once again, there's a bazillion trig examples. Trig's in almost every question these days. You need to know your unit circles well. You need to be able to do your inverses pretty quickly. You don't want to get too tangled up in them. All right, any other questions on that? Going once, going twice, gone. Let's do a random access then. So this will show Ari what he was looking for. So shell method around another line. So we've got this region right here in the xy plane. It's generated from x squared, 1 and 0 there. And we're going to rotate about this axis over here. So there's our axis that we're going to rotate around. If we've got our basic geometry understood, it's not going to be that big a deal. If we remember, especially our 2 basic facts, that a vertical distance is upper minus lower and a horizontal distance is right minus left, those 2 facts really tell us everything. So let's go ahead, and we are going to use the shell method. So our basic formula for the area of a cylinder or a shell is 2 pi RH. So let's look over here at our picture and see if we can identify that stuff. Here's our region. It's being rotated all the way around the y-axis. So the element that I've chosen is vertical because it has to be parallel to the axis of rotation. That's how you create a cylinder. To create a cylinder, you have to have a parallel axis and element. And the height of our cylinder is going to be the height of that red segment. That'll be the height of the corresponding cylinder. We are going to say that this vertical element is at a random x value. So we'll say that's the element at x. The radius, well, that's just the distance from the axis of rotation to the element. That's the radius. That's going to be the radius of the cylinder that's going to be created when we take this and rotate it all the way around the y-axis. Okay. Now, vertical element. So is our integration variable x or is our integration variable y? Are we going to use a dx or a dy? Dx. So you can think of that in a couple of ways. For some people, it's easiest to say, okay, well, I see this rectangle here. The thickness of it is dx. Right? The thickness of it is in the x direction, so that's a dx. That tells us we're going to integrate with respect to x. Another way is to say, oh, this vertical element is sliding through an x interval, so we want to sum up a bunch of rectangles that are sliding in this direction, which means I'm adding them up with respect to x. So you can think of it in a couple of different ways. So that tells us the r and the h need to be turned into x's, because we want to have a dx that matches them. So let's go ahead and look over here at our function. The curve here for the height, that upper curve, so this curve right here is y equals x squared. The lower curve down here, oh, that's just y equals 0. That element is vertical, so we do the upper y minus the lower y. All we need is the x squared minus 0. We don't need to put the 0 in there. So that's going to be the height. 2 pi. I'm going to leave a blank for the radius. And then the height is just that function, x squared. Now let's do the radius. The radius is a horizontal distance. Whenever we do a horizontal, we do right minus left. Right x value minus left x value. So let's come over here and take a look. The left x value is over at -2. So here's the left x right there. X is -2 right there. The right x for this element is what? This element is right here at x. If we're trying to measure the distance, we're trying to measure from here all the way over to here. The x value right here is just called x. The x value over here is called -2, so we do right minus left, so it's going to be x minus -2. And that'll give us x plus 2 when we simplify it. The other way to visualize it is that when you look here, you can say, oh, this distance right here is 2. And this distance right here is x. So the total distance is x plus 2. So you can think of it that way also. Does not matter which way you think of it. So we're going to have 2 pi. 2 pi multiplied by, if we distribute the x squared, we're going to have x cubed plus 2x squared. And the rest is pretty straightforward. The hardest part we've done. So is there any piece of that setup that you're not sure about? So once we have the setup, then it's the rest of it should be fairly straightforward unless unless you're given a nasty integral. But for the most part, the rest of it should be pretty straightforward. The hard part in most Calc 2 problems is the setup. So limits of integration. What are the x values for the interval? Zero to 1. So when we look over here, this region is what's creating our solid object, and the x values for this region go from 0 over to 1. So those are the limits of integration. We're imagining a cylinder for all of those x values that are in between 0 and 1. So 0 to 1 creates all of the cylinders, and then the integral adds them all up. So we will have 2 pi multiplied by x to the 4th over 4 plus 2x cubed over 3 from 0 to 1. And plugging in 0 is not going to contribute anything. So we have a 4th plus 2/3. So that's going to be 2 pi multiplied by 11/12, which will be 11 pi divided by 6. So that is the volume going around a random axis. Any piece of that you want to ask about? So let's take that same region and let's rotate it vertically. Let's rotate it around y equals 2 instead of horizontally. And let's see what happens. So once again, we have the area of a cylinder. That's our basic geometric shape that we're using. So that's 2 pi times r times h. The axis of rotation is horizontal. So that means we need to choose a horizontal element so that when it rotates around, it creates a cylinder. And as soon as we have a horizontal element, we know that the integration variable is y. So we're going to have a dy, which means the r and the h need to be turned into y's. They have to be written as functions of y. Let's label stuff. So our height is sideways now. It's that distance between those two curves. The radius is vertical. It's the distance from the axis of rotation down to the element. The curve is y equals x squared. This vertical line is x equals 1. Let's go ahead and substitute. So for the radius, what do we think for the radius? What do you think for the radius? Awesome.
2 minus square root of y.
2 minus square root of y? What do we think? So for the radius, so I agree with your upper, so first of all, a vertical, upper y minus lower y, your upper y is perfect. The upper y value right there. Now the lower y value, so this element is horizontal, so don't we say that that's a random element at a height of y? So what would your lower y value be? See? Just y? Just y? So the 2 minus, what did you say originally? 2 minus?
Square root of y.
2 minus square root of y. So you were measuring more down to the curve instead of to the element. So to get all the way to the element, that upper y value is 2. The lower y value is y. So 2 minus y is the radius. And how about the height? So the height is sideways. Sideways is right x minus left x. The right x is 1. Okay, the left x, oh, the curve is written as a y, not an x. It's written as a y value. So we need to isolate x here. And what is x going to be as a function of y? Root y. So the height then is the right x minus the left x, so it's 1 minus the square root of y. Bless you. Do we have agreement? So we certainly benefit by having a picture and figuring out kind of what the relationship is between all of the boundary curves, the element, and the axis of rotation. But it all really does boil down to upper minus lower or right minus left. In order to integrate, we're going to have to FOIL this out. So we're going to FOIL, we're going to get 2 minus 2 root y. So 2 root y minus y plus y to the 3/2. So that is the area of the cylinder at height y. So the volume is then the integral of that. So we'll integrate this function. Integrating with respect to y. How about limits of integration? 0 to 1, and are those coming from the y-axis or the x-axis? Mm-hmm. Very good, from the y-axis. So 0 to 1. So that integration interval is coming from over here, right? We're integrating in here. We have y values from 0 to 1. This standard integral with polynomial type of evaluation. We'll get 2y minus. We have a y to the half. We add 1 to the exponent and get 3/2. We're going to have 2. We get y to the 3/2. And then dividing by 3/2 means multiplying by 2/3. Over here we get y to the 5/2. Divided by 5/2 means multiply by 2/5. And then those y values are from 0 to 1. Now we're just going to plug in the 1. Plugging in 0 gives nothing. So that's it. And you know how to do this arithmetic. We won't do the very last step. You can find a common denominator and add. All by yourselves. All right, anything you want to ask about? Any questions, comments, insights? All right, we'll go to the napkin ring. I've always wanted to know the volume of a napkin ring. So we've got this napkin ring type object. You know, it's a sphere with a hole drilled out in the middle of it. So the one that we have here, we're going to drill out a hole of radius 3 symmetrically through a sphere of radius 6. So this is looking down from the top. Top view shows this circle of radius 6. There's the circle of radius 3. That's the hole being drilled out. This is kind of a vertical cross section to get a sense of it. And to create the napkin ring, we're going to take this shape right here, this crescent shape, rotate it around the y-axis, and that's going to create the whole napkin ring from that region. So this was of radius 6. Radius 6. So this equation here for the outer circle is x squared plus y squared equals 36. That's the equation of a circle centered at the origin. X squared plus y squared equals the radius squared. All right. If we are going to use cylindrical shells, I'm going to break it apart with symmetry. I see that above the x-axis here, this region here will rotate around and create the top half of the napkin ring. The lower piece would rotate around and create the bottom half of the napkin ring, and they're symmetric. So let's just focus on the top, and then we'll double it. So if we take this region in quadrant 1, rotate it around, and double it, we'll get the total volume. Okay, now we're using cylindrical shells. So here is our element that has a height of h, and the radius is going to be the distance over. Whoa, interesting. Didn't see that coming. And the radius is going to be that distance from that vertical element to the axis of rotation. Okay. So we are going to look again at our generic formula. Generic formula, the area of a cylinder, 2 pi RH. Do we integrate with respect to x or y in the end? Because this is the random element. We're drawing a representative element. It's just random. We're going to say it's at x. So vertical element at x. Oh, man. Thought I had it figured out. So we need to convert the r and the h into x's. And that's pretty easy in this case. We have, for the radius is x. That's how far the element is from the y-axis. Now the height, that's vertical. So a vertical distance is always the upper y value minus the lower y value. Well, the lower y value is just 0, right? The lower y value down there, the y value there is 0. The upper y value right there, the upper y value right there, that's coming from the top half of the circle. Right? If we take the circle and we isolate y, that means y equals something. That's going to give us the top half of the circle. So we're going to have to come over to our circle, isolate y, and choose the positive square root, because we want the top half of the circle. The bottom half of the circle would be the negative square root. So the equation right here of this curve written as a y value, that is going to be y equals the positive square root of 36 minus x squared. So that is that y value at the top of that element. So again, we're doing upper minus lower. The lower is just 0. So no biggie then. The height is that. So now we have the area of the cylinder at a height of y. Excuse me. We have the height. We have the area of the cylinder at an x value, where x is any of these numbers in between here. So we have the area of the cylinder as a function of x. So if we plug in any of the x values, we'll get the corresponding area of a cylinder. Now to get volume, we integrate area, but we're going to have to double it, right? So we just did the top half here, so we have to double it. So it's going to be 2 times 2 pi. And then we'll put this stuff inside the integrand here. And our limits of integration. What do our limits of integration go from? So almost 4. So 5 is right here. This thing is of radius 6, so 6 is there, but this is 3. And we had a thing of radius 6, and we took out a thing of radius 3, so we're going to go from 3 over to 6. All right. Now we get to use substitution. And remember that substitution always works if you let u be something, usually u is fairly obvious. Usually it's what's in a square root, up in an exponent, inside an angle. the natural thing to try before anything is to look inside and say, oh, well, let's get rid of this. Right? The square root of a difference, you can't break it apart. Right? That square root is indestructible. You can't break it apart and take the square root of 36 minus the square root of x squared. You can only separate a square root if it was multiplication or division. So we can't separate that. So the idea of letting u equal what's in there and combining into one thing is a good idea. So let's go ahead and let u equal 36 minus x squared. And then we want to take the derivative of both sides. And we get that. The derivative of 36 is 0. The derivative of negative x squared is negative 2x. And there's lots of ways you can do this. I'm just looking inside this integrand right there, and I see x dx. If you wanted to, you could pull in one of these 2's to make it match better. Doesn't matter. Lots of ways. So what I'm going to do over here is rewrite this as du divided by negative 2 so that the right-hand side now matches exactly what's inside that integral. So now the greens match. So we can come in here now, and we're going to have 4 pi out in front, the integral, the square root of u, and then x dx is du over negative 2. So we've converted from x's to u's, which means we also can convert the limits of integration so that we don't have to go back to x in the long run. Sometimes that's easier, sometimes it's not. It kind of depends. So let's do a limit conversion. When x is 3, what is u equal to? 27. And when x is 6, 0. Yep. So that's where we're at. Let's pull the constant out front. So we're going to have negative 2 pi integral 27 to 0 square root of u du. The limits of integration feel backwards because usually we think of the lower limit of integration as being the lesser number. If we wanted, we could do this. Couldn't we just switch them and then convert the sign on the outside? You don't have to, but there's going to be less sign issues if you do this. And then we'll think of u to the half as the representation of the square root of u. And now we're good to go. So now we've got our multiplier in front, 2 pi, and we have u to the 3/2. I'm going to leave a space for the 2/3 multiplier. 0 to 27. Yeah?
Since. Oh, wait, I'm sorry, I didn't see.
No problem. So we're going to have 4 pi divided by 3. 0 gives nothing. So now we have to fiddle around with this 27 to the 3/2. Let's just come over to the side for a minute. So 27 to the 3/2. Again, it's easiest usually if you implement the denominator in that exponent because the denominator is a root, which will make the base smaller. So we want to take the square root of 27. The square root of 27 is 9 times 3, so that's going to be 3 root 3 cubed. So then if that's cubed, we're going to take 3 root 3 and multiply it by itself 3 times. I'll just write it out for once. So we've got that. So that's going to be 20. It's going to be 3 times 3, which is 9 times 3, which is 27. Root 3 times root 3 is 3. And then we have 1 root 3 left over. So we're going to get that. So we're going to get 81 root 3. So that's one way to evaluate that 27 to the 3/2. We're going to see a lot of 3/2 power, so it's going to be helpful to be able to evaluate these. Here's another way, which I think is actually easier. So you could do this also. So 27 to the 3/2, you could say that is the square root of 27 cubed. Well, the square root of 27 cubed is 27 root 27. You're going to cube the square root. Like if you take the square root of 5 and cube it, you'll get 5 root 5. If you take the square root of 2 and cube it, you get 2 root 2. Because you're taking root 27, multiplied it by itself 3 times. Well, 2 of them multiplied together give you that. And then we simplify this. That's 3 root 3, and 3 times 27. So we're going to get that. So 3/2 power, you're going to see it a lot. You just make sure you're good with exponents and how it affects everything. So then we're going to come over here, and we have our 81 root 3. Simplify that. So what is that, 27? So 27 times 4 is 108. 108 root 3 times pi, if I did my arithmetic right. Which I'm sure someone's going to check. Good. Thank you. So we've got that. So there's, again, frequently you're going to see these things like this. Let me write one that doesn't have the extra simplification step. So if you're thinking about this, you're going to end up with root 5 multiplied by itself 3 times, which is 5 root 5. So that is the standard way that we usually simplify a 3/2 power. Standard. Yeah?
If you scroll up a little bit, when you are on the step of the 4 pi with intervals over 27, all that.
Yep.
How do we get to -2 pi again?
This -2 pi
Yeah.
is this constant 4 pi divided by this constant -2.
Why do we not divide square root of u by -2?
Because this is a product, so it doesn't have to be distributed.
Got it. Okay.
Does that make sense?
Yeah.
If you have something like a times b times c divided by 2, you only push it into one of them. Right?
Okay.
Like if it was a plus b plus c, then you have to share it and distribute it. But if it's multiplication, you can just group it with one of them. So that -2, it's all multiplication in the top, so I just need to combine it with one of them. I'll combine it with the constant out in front. Any other questions you see on it? All right, so let's go to 6.5. And in 6.5, we are going to be dealing with the length of curves. So finding arc length, all right? It's a sphere with a hole drilled out in the middle. Because that's, in the old days when people used cloth napkins, you would roll up the cloth napkin, you would pull it through that little sphere with the hole on it, and it would just sit neatly on your table. Napkin ring. Most of us don't use napkin rings anymore, if ever. Just like we don't use cufflinks anymore. Or analog clocks usually. You ever know what a cufflink is? They have the shirts that the button, instead of a button, you had a little fancy silver thing that went through and twisted and kept your shirt from going up. Yeah. So napkin ring is just the old cloth napkins. Yeah. Which most of us don't use either. Okay. So let's look at some basic ideas for arc length. So one thing is that we use the letter S to measure distance along a curve. I forget why, there's some Latin word that begins with S or something. But normally in math, we're going to use S to represent distance along a curve. And it would be super easy if we had an S number line. Like if we had a number line that was twisted along the curve and you could just count along that S number line. We don't have that. In our coordinate system, we know all about X, we know all about Y, but we don't have a number line that's twisted onto that curve, so we can't just look at the tick marks on that number line and figure out how long a piece of arc is. So we have to use the X's and the Y's to get there. So what we do is create this little differential triangle. And the differential triangle is the same differential thing that you did in Calc 1. In Calc 1, you said that dx was always the same as delta x. So delta indicates an exact distance. It's not an approximation. So delta s represents the exact distance along the blue arc. ds is approximating that delta s. All right. So in Calc 1, you said that dx and delta x were the same, but then delta y, which was the exact y change, was approximated by dy. And you had that equation, dy equals f prime of x dx. So that's what you did in Calc 1. The generalization of that here is that we're focusing on the s. The dx and the dy are going to represent independent variables. And just like in Calc 1, where you said delta x and dx are the same, you always set the independent increment, the delta means increment, the independent increment and the independent differential, you always set them equal to each other. So delta x and dx were the same. But the dependent was an approximation. dy was approximately equal to delta y. Same idea here. We're going to say that dx and triangle x, so increment of x, are the same. dy is also going to be an independent variable, so dy and delta y will be the same. But the dependent variable will be s, and the differential in s will approximate the increment in x. So that's kind of just a little background on it. In practice, we don't really have to think that hard. So let me show you what I mean by that. So if we were trying to find the distance along the arc, we would be adding up all of these little ds's along the curve. But again, we don't know anything about these limits of s. We don't know what this s coordinate is. We don't know what that s coordinate is. If we did, we'd be done. If we were going from s equals 1 to s equals 6, that distance would be 5. But we don't know the s values. We don't know anything about the numbering along the blue curve. So what we have to do in order to evaluate this integral is replace the ds with something we know. We know x's and y's. We see that right triangle up here. That right triangle, we go to the Pythagorean theorem, solve it for ds, and what we want to do at this stage, a little bit of arithmetic or algebra, that's not going to help us if it's inside an integral. We need to have a dx or a dy at that tail end so we can integrate with respect to x or y. If we factor the dx squared through the square root, it'll come out as a dx. But this dy, there's no dx here, so the idea is that we're going to multiply this second one by dx squared over dx squared. And when we multiply that one by dx squared over dx squared, the dx squareds are common. They factor to the outside of the square root as a dx. And then we're left with dy squared over dx squared, which you can rewrite as dy dx quantity squared. And you know what dy dx is. Dy dx is f prime. It's y prime. It's the derivative. So that is how we generate this arc length formula. So you can write dy dx as y prime. I write it as y prime usually because it's less work than writing it as x prime, f prime of x. You can write it as f prime of x. You can write it as y prime. You can leave it as dy, whatever you want. Doesn't matter. 3 different notations for the same thing. That's what we do in math. So that is our arc length formula. So arc length formula, we integrate the square root of 1 plus the derivative squared. Let's take a break before we do any arc length though. Let's take 10, and then we'll do some arc length when we return. I will restart my login and see if I can.
It does the same thing in my engineering class.
So
Flicker?
what we figured out though is that if you turn on the TV first, it shouldn't do that. And so I think I logged into the computer. All right, so let's go ahead and do some examples of arc length then. So our formula, our new formula is right there. And again, it's your choice whether you use y prime or f prime or dy dx. I don't care. It's up to you. Whatever you think is best. So there we go. So we've got a curve, super easy curve. In order to find arc length, we need that curve's derivative. So that's the first thing I'm going to do. I see that I need the derivative. So we're going to take y prime. And what's y prime in this case? -3. So y prime is -3. And we're told that we want to be on the interval -3 to 2. So that -3 to 2, if we look down here at the x-axis, -3 to 2, we're right here. So that's our integration element, our integration axis coming from the x's. So then, okay, like that. Over here. Now it, nope, still doesn't like it. Okay. So our limits of integration are going to be -3 to 2. And we're going to have the square root of 1 plus 9. 1 plus y prime squared. So 1 plus 9. This will give us the square root of 10, which can be factored to the front. We've got that. And this is the square root of 10 multiplied. Anyone know what that's multiplied by? What that constant is? 5. So we get 5 root 10. So everybody see, so this integral part, does everyone see why that's equal to 5? So this is integrating just the differential dx. So this is saying, oh, what is the arc length on the x-axis from -3 to 2? Well, it's the right number minus the left number, 2 minus -3. So the integral of a differential, if you know the limits of integration, you just do the subtraction. Up here, if we knew an S1 and an S0, we could just subtract them, but we don't know S values. But down here, we do know the X values. So now if you wanted to do it the long way, you can keep going. And what is the integral of dx? If you were going to integrate 1 dx. It's just x. And the limits of integration are -3 to 2. So then you're going to have 2 plugged in as the upper limit minus the x minus -3. And so that's going to give us the same answer, 5 root 10. Yeah, 5 root 10. So as you do more and more, you'll start to just jump from there to there. It's like, oh, if you're integrating just the differential, it's the upper limit minus the lower limit. It's the length of the interval. So there is our arc length. Let's try another one. So there's a bunch of gnarly ones in here that you will hate. I'll try to help you navigate them so that you hate them less. These are the two perfect square trinomials that you have seen since college algebra, or since before algebra, I guess, before college algebra. So these are trinomials because they have three terms. That's how the two of them factor. So the trinomial, the perfect square trinomial with the minus factors into that. Perfect trinomial with the plus factors into that. If you FOIL this back out, you would, go the other direction. So just keep that in mind. Notice that if we have this perfect square trinomial with the minus, if we only change the sign from negative to positive, then all of a sudden the factorization is the same, except that we have a positive instead of a negative. So just keep that in the back of your mind. If we did something to only change the sign of this middle term, then we just factor it with a plus instead of a minus. So keep that in mind. All right, so here we've got this curve. We've got our function. We've got our arc length formula. We need the derivative of the function to put inside that square root. So let's do that first. So we're going to come up here and differentiate before we do anything else. So we're going to have y prime equals 3. The derivative of natural log x is 1 over x. And then we differentiate over here. We bring the 2 down and subtract 1, giving a 1. When we bring the 2 down, we have 2 over 24, so that can simplify to 1/12. So we're going to have x divided by 12.
Will
So
they
there.
always give up, do the terms that you're doing it from, so 0 to 2 or 1 to 6 in this case?
Yeah, because when we find arc length, we need to know from where to where, right? So if most curves are going to go on forever in at least one direction, so we have to somehow indicate where you want the arc from. So yes.
How did you know the x squared divided by 24 was within bounds of the log?
Well, this is a separate, say that again. So that x squared over 24 is separate from the log. So it's separate from the log. So when we differentiate term by term.
But how did you know? Because there's no parentheses.
If there's no parentheses, it means it's not on the inside. So you were saying, how do I know that it's not this?
Yeah.
And only because when we write logs, if we wanted that second term included, it would have to have parentheses. So if there's no parentheses, it means that if there's a plus or a minus, that anything out there is not in it. Yeah, good question. So our next goal is to square that y prime. And let's square it outside. Let's square it up here where we have plenty of space. So we want y prime squared. Now here is where, let me write it out first and then give you some warnings. So it's super tempting, very tempting, to square it, to expand this thing and to be simplifying as you go. Like 3 over x squared is 9 over x squared. That is what you do not want to do. So what we are going to do is look over here. When we have a minus b squared, we're going to leave it in this type of setup. Instead of simplifying each of these individual terms, just leave them as they are. So in other words, I'm going to write this as a squared, so 3 over x quantity squared. Yeah, I know it's 9 over x squared, but don't do it. Just leave it like that. And then it's going to be minus 2 times. Keep in mind that this is a, and this is b. So a minus b. The b does not include the minus sign. So it's a minus b, and then we just plug it in. So then we have 2 multiplied by a times b. So a is 3 over x. B is x over 12. And then plus b squared. Okay, so that's written super generally. We didn't simplify each step as we went. So a minus b squared is a squared minus 2ab plus b squared. All right? So now let's come down here and look at our integral, and it's going from 1 to 6. So those are given, 1 to 6. Big square root here, and it's going to be 1 plus. So I'm going to simplify only the middle term here. So we're going to simplify just this. So as we pull it into the square root, we're going to simplify just that part. Okay, all will be revealed. Don't panic. So we're not going to simplify that a squared. This we're going to simplify to, and we notice that this all simplifies to negative 1/2. No, we're not going to simplify this. Does everybody see that that simplifies to negative 1/2? We have an x up top, an x down below. Those cancel each other out. 2 times 3 is 6. That's living in the numerator. 6 over 12 is 1/2. So here is the crux of the problem. When we add this 1, notice what happens. So we've got this right here as our perfect square trinomial. Right? We started with a minus b squared, and we turned it into this, so that's a perfect square trinomial. Right there. And we know how to factor it because it came from here. That's where it came from. So that's its factorization. Not obvious. If someone gave you that straight out of the gate, it might not be obvious how to get to there, but you could. Now look at what happens when we add 1. When we add 1, the only thing that changes is the sign of the middle term. All right? This perfect square trinomial right there, this perfect square trinomial right there. The only difference is that we went from this to this. That means we know how to factor it. If we have the factorization for this one, and all we do is change the sign of the middle term to plus, then we know the factorization of the second one. So that can be factored into, instead of a minus b squared, it's a plus b squared. Tracking? Not tracking. So, and I put that in the wrong place, so it's a minus turns into a plus, b is that, quantity squared dx. So we started with a minus b, squared it out and got that, simplified the middle term, and then we had to do this little addition of 1 because that's what the formula says to do. It says add 1. So then we added 1, and the adding of 1 created the exact same expression as our original perfect square trinomial, except that instead of a minus we have a plus. That means we know how to factor it. And what's the square root of a square? They cancel. Right? Cancel. I guarantee you, if you were to multiply this all out, you would just get lost in the shuffle and you would never even notice that it was a perfect square trinomial, let alone what it would factor into. It's very easy to think you're doing the right thing by canceling common factors and doing all that stuff, but in this case it's not. So we have 3 over x plus x over 12 dx. So there we have it. This is easily integrable. What's the integral of 1 over x? ln of absolute value of x. So we're going to have 3 multiplied by ln absolute x. And then the integral of x over 12. add 1 to the exponent, giving x to the 2, divide by 2, mash it with the 12, get 24, and that's going to go from 1 to 6. And then we just plug in our upper limit, plug in our lower limit, and we're good to go. So we get 3 natural log of 6, then plus 36 over 24, which reduces to 3/2. And then we subtract off antiderivative at 1. Natural log of 1 is 0, so that's gone. We subtract off 1/24. And now I wish I didn't simplify this one. I'm going to go back to 36 over 24. So then our final answer, we have 3 natural log of 6 plus 35 over 24. All right, so there are a bunch of those in the homework and quiz with these perfect square trinomials. If there's one on a test, I will tell you that it's the perfect square trinomial one so that you don't go down the wrong path.
If you don't tell us, so how can you figure it out by just looking at it?
So the pattern, if you're looking at a random arc length, to know that it's a sneaky perfect square trinomial, you're going to see this. You're going to see that, okay, when you FOIL out the derivative of your original function, and then you add 1, you are going to see that the only thing that changed is that sign. So if you, and the only way this can happen, with our arc length formula, we're adding 1. So the only way this can happen is if that happens to be a -1/2 in the middle. Because the only way adding 1 is only going to change the sign from negative to positive. The only way is if, when you're adding 1, is if this started at -1/2. Any other middle term here, when you add 1, is going to do something other than just change the sign. The only real number, when 1 is added to it, only changes the sign, is -1/2. So if you get a -1/2, when you do the y prime squared, if the middle term reduces to -1/2, you know. Then it's a perfect square trinomial. Okay, let's try another one. These take a little bit of practice. So, same setup. Our arc length formula, 1 plus the derivative squared inside the square root. Now, if we have functions of x, the formula has a dx and a dx. Notice that this one that they give us has a y. So it's a function of y instead of a function of x. So all we do is change the dx to a dy. And instead of a y prime, we do an x prime. So same pattern, just that we change the role of x and y. So we're sitting right there. So here's how we're going to know that it's a sneaky perfect square trinomial. So we're going to take the derivative. We need x prime. So first we take the derivative. The 4's cancel, so we get y cubed. And then this one is 1/8 y to the -2. So we're going to think of it like that when we differentiate. So the -2 comes down, so we have -2 divided by 8, which is -1/4. Y to the -3. Subtract 1. Not add 1. Subtract 1. So we have this. So there is our a minus b. And then we need to square this. So here's where I'm saying don't simplify, just leave this as is. So we're going to have a squared minus 2 times A times B plus B squared. Let's not simplify the B squared. Just write it like that. So A minus B squared. And let's focus just on the middle term. When we focus on this middle term, what does it all simplify to? -1/2. That's how we know it's going to be one of these weird perfect square trinomials. So we have that the y cubed times y to the -3, that becomes a 1. And then we have 2 divided by 4, which becomes the 1/2. So that's the x prime squared inside the square root. So now we have to add 1 to this. Right, now we have to add this 1. We haven't added the 1 yet. And when we add the 1, we see, oh gosh, the only thing that's going to change is the middle term is going to become +1/2 instead of -1/2. So that tells us that the factorization of it that came from A minus B squared is going to turn into A plus B squared. And what were our limits of integration? 1 and 2. So let's write down our arc length is going to be integral from 1 to 2, square root. There's the x prime squared. Now we have to add 1 to it. So I'm going to just add the 1 to it and change the sign of the middle term to +1/2. So we have that. So we added 1. And as soon as we see that we're dealing with a perfect square trinomial, we started here with A minus B. The factorization is going to end up being A plus B squared. So we're going to get y cubed, there's A, plus B, which is that one, quantity squared, dy. A plus B squared. And remember that the A and the B, they don't include the minus. So it's A minus B. That factors into A plus B squared. The square root and the square go away. So then we're left with something easily integrable. So we're left with y cubed plus 1/4 y to the -3 dy. Can we integrate with the power rule? Y to the 4/4. Y to the 4/4. Okay. We add 1 to this exponent, we get -2. So we get y to the -2. We divide by -2, giving -1/8. Whew. Plug in the 2, and we get 16/4, which is 4. Plug in the 2 here, that's 1/4, so that's -1/32. Subtract the lower limit. So we'll get that. Common denominator of 32. So we're going to have, what, 128 minus 1 minus 8 plus 4. 32, that's 119, 123 divided by 32. If the arithmetic is right, we're there. All right, questions on any step? Any funny business? Anything driving you crazy? Good. All right.
So since we currently can't derive it when there's not a single thing, or there's more than one thing under a square root,
Mm-hmm.
does that mean these are like all gonna be either simple or the perfect ones?
Yes. Because, so, the integral of a square root, we can't separate a square root across a plus or a minus. So either it's got to be totally cooked up so that we can get rid of the square root, or what's inside here has to allow us to integrate. And we'll see some cases where it will work out that we can integrate it. Yeah. Tricky stuff. Okay, you guys try this one. This one is not a perfect square trinomial, it's much easier. So try this one and see if you can work it out. So the function is given to you as a function of y with y limits. There's the picture, there's the formula. So this is one that you can integrate.
It's hard.
Yeah.
Yeah.
Yeah, Calc 2 is hard. To tell people I'd like to say, please do Calc 2. It is just as much work.
Yeah.
At the same time.
He's doing 3 now. He did 2 last semester. He's just here for some extra fun.
Yeah. People said 2 was harder than 3. 3 is hard. Still.
I know. More different. Do we know if you're snagged on anything? First dollar you ever made? Oh, cool. Da. Actually, I should take roll while we're doing this. Daniel is here. Jordan has seemed to have vanished. Ryan is here. Lauren is here. Caitlin is here. Aiden is here. Maddox seems to have vanished. No Maddox, right? Harrison's here. Austin is here. Caitlin is here. Landon returned. Alex is here. Hui is here. Carter is here. Jose is here. Arenas is here. Yanel is here. Anna is here. Deepa is here. Gage is here. Ari is here. Yeah, you can do these. Yep. Subjected. Or there's a clever way to do it with reverse chain rule. If you want to try to be clever. If You want to try to do
It
that.
works so well.
Yeah, now use your sub or reverse chain rule. Because that substitution would be linear. So you could use, I'll start writing it down up here. Try to catch up to you. Try to catch up. That was
Not the
terrifying.
flicker.
I can't believe we've gone from no flicker to flicker in a heartbeat. Yes. Yeah, let me get this going. We'll get there.
Yeah, and then.
Let me catch up to you.
I haven't started.
Oh, you haven't started
No,
it?
because I don't, there's a step in that I'm not understanding.
Yeah.
I'm not understanding how there's 1/2 of here to here. And
Factoring.
So we're factoring now.
Yep, so this is a trinomial,
Yes.
and that's what it factors into, which seems, it's not obvious. So when you start up here, you have A and you have B, and you square that out, so now you're foiling. You get to
Yep,
this.
okay, I get that, yep.
And then when you, so there it is, that's the foiling of that. And when you add the 1, now the only thing between here and here that's different is that's plus instead of minus.
Okay.
So that means it factors into A plus B instead of A minus B. So this whole thing factors into this,
Because it's a positive and this is originally
a minus.
minus.
So if you were to take this and square it out foiling, you would get this.
Oh, okay.
Does that make sense?
Yes, now I understand, thank you.
Yeah. Okay, so S, they give us limits of integration, 0 to 4, square root. So here is where I saw a lot of you, right at that stage. So you can either use substitution or reverse chain rule here. If you use substitution, what will you let u equal?
The whole thing.
The whole thing inside the square root, right? Yeah, so you can do u sub doing that. Or as you've seen, when you have a linear substitution, that's linear, you can use reverse chain rule. So here's how I would do it with reverse chain rule. I'm thinking, okay, 1 plus 9/4 y to the 1/2. You add 1 to 1/2 and get 3/2. You divide by 3/2, which means multiply by 2/3. But then we have the RCR piece. We have to do what with 9/4? Divide by 9/4, which means multiply by 4/9. So that part right there is how we could do it with RCR instead of use substitution. But you will get the exact same thing. Okay, so this is going to be 8 over 27. And we still have our limits of integration 0 to 4. 8 over 27. 1 plus 9/4.
She said she likes substitution better.
So that's where you should be at if you did your u sub right. What's the question here is the derivative. So that is coming down. So subtracting 1, so you have 2 over 3 minus 3 over 3, so that'll be minus 1 over 3.
That's the equation for
So we get that. Oh, yeah, you subtracted 1 wrong. Wait, or,
U is just.
oh, you have a different problem?
What?
Oh, you wrote 2/3 instead of 3/2.
Oh.
That'll make it different. That'll make it different for sure. That was starting to be. Is 3/2 minus 1 or 2/3 minus 1? It makes a big difference. Okay, so then there's our final antiderivative, and then we just have to plug in our limits of integration. So this is going to be 10 to the 3/2 when we plug in a 4, minus 1 to the 3/2 when we plug in 0. And we talked about this earlier today. We see a lot of problems in this class where we end up with a 3/2 power, and our typical way to simplify it is like that. So 10 to the 3/2 is going to be 10 times root 10. Austin?
Okay, for the highlighted step.
Yep.
Is there a reason why it's 2/3 times 1 plus 9/4
I'm sure there is.
instead of 3/2?
So when you do the power rule, you add 1 to the exponent and divide by the new exponent. So if you add 1 to 1/2, you get 3/2. And when you divide by 3/2, you flip it and multiply by 2/3. Make
I
sense?
just didn't see that, my bad.
Yeah, yeah. So when you divide by the fraction, you multiply by the reciprocal. All right, let's go to another one.
Wait, can you?
Yeah. So the arc length section is kind of short. There's not a lot of problems because you guys kind of pointed out either the integrand has to be super easy where you can use substitution or RCR, or it's got to be that perfect square trinomial. So there's not a lot of variation. It's going to be one of those two. So that's why this section tends to be very short. All right, so here is another one. Let's go ahead and that one is not a perfect square trinomial, so let's do one more that's not. So we're given a function of x on an x interval, so we're going to have the integration formula will have a dx. Let's go ahead and find the derivative. So we need the derivative in order to get to the arc length formula. 3/2 times 2/3 is 1. So we're going to have x squared plus 1. We're subtracting 1 from this exponent, giving 1/2. And then what do we have to do next to finish off the derivative? Chain rule. So the inside has an x squared in it. It's not just an x, so we have to then modify it by multiplying by 2x. So there's the derivative. We see in our arc length formula that we have to find the derivative squared, so now we're going to square this. And if you square a product, you square each factor in the product. So if we're going to square this, we can square the first part and get x squared plus 1. Square the second part and we get 4x squared. So if we square a product, we square each term, each factor in the product. All right, and then we can combine this together, so we're going to get 4x to the 4 plus 4x squared. So let's go ahead and build our arc length formula then. So S is going to be integrating from 3 to 9, square root. We have to add 1 to this thing. So we have 4x to the 4th plus 4x squared plus 1. So, like we pointed out, we can't separate that square root when there's pluses and minuses below it. So the only hope of integrating this, the only hope is that that is factorable and can turn into something squared so we can eliminate the square root. That's the only hope. Let's check. Is it a perfect square trinomial? It's not a sneaky one, it's just a regular one if it is. So let's see, 2x plus 1 squared. Is that it? All right, so we get 2x quantity squared is 4x squared. 1 squared is 1. The middle term is going to be 2x times itself. So 2x times itself. Did I factor that right?
Is it 2x squared? Yeah, 2x squared.
Thank you. Something was wrong. It's got to be 2x squared because that's 4x to the fourth. That's 1. A times b is 2x squared, and then we double it and get 4. So yeah, thank you. What is happening? And that then reduces the integrand beautifully. The square root and the square disappear. We get 2x squared plus 1. Square root of the square. So then we have something that's pretty easily integrable. So oh my gosh. So this is going to be, when we integrate, we're going to get 2/3 x to the 3 plus x. And that will go from 3 to 9. Plug in the 9, plug in the 3, take the difference. So what do we end up with? 2/3 times 9 cubed plus 9 minus 2/3 times 3 cubed minus 3. And whatever that all multiplies out to. Whatever that turns into will be our answer. So that one's not too bad. It's not totally cooked up to be a sneaky perfect square trinomial, but we did end up with a perfect square trinomial on the inside. Any step there that you're curious about? All of them? None of them? All right, let's see. So we have one more that's a sneaky one there. And what's this last page is the... Let's go ahead, and I just want to point out, I'm going to pass on that other perfect square trinomial. We can do it next time. I mentioned this last time, some integrals may look easy to integrate, but they're not. And so that's what this is all about, integrating with the calculator. And we'll just do a couple where we have to integrate, where we can only approximate with a calculator. So we know that we need to take the derivative. We plug it into our arc length formula. We're going to integrate from -1 to 1, the square root of 1 plus x squared. And we have that. That is something you can't integrate yet. So at this stage, if what's inside the square root is linear, you can integrate it. But if what's inside the square root is a sum of squares, you can't integrate that yet. So this we would have to use a calculator. And all of the graphing calculators, Desmos, all these technologies, they can all do these types of integrals really easily. So we'll just do it in Desmos. Whoa. How did I just open Desmos randomly off the web and have a function already in it? That's weird. That's bizarre. I just went to desmos.com and there was a function in there. That's weird. Okay, 1 plus 4x squared, square root. So square root, SQRT, 1, oh, I forgot the integral, 1 plus 4x squared. And we need a d. We need a dx. And how do you think you make the integral symbol?
INT.
INT. And what were the limits? 1 to?
-1 to 1.
-1 to 1. Thank you. And there it is. Super easy. So if you don't have something that's integrable, that's all you have to do. So all the graphing calculators can do that. Good way to check your work, obviously. Very helpful. So similarly here, why don't you guys do this one? So take the derivative, set up the integral, and then plug it into your device and see if you can get the correct approximation. See if you can do it.
So we're going to be one like this on the exam.
Yeah, there won't be one like that on the show. Just the homework, yeah. Good question. There won't be.
I don't have a graphing calculators.
Yeah, you can't use graphing calculators on the exam, so one of these won't be on the exam. Did I square something wrong there? What did I do there? Did you all get 4 minus 2x as your derivative? And then when we square it out, we get 16 minus 8. What did I do? Minus 16x? Minus 16x. Can someone someone confirm? Is that what y'all got? Yeah. Thank you. Anyone have trouble on their device? That's fine. Yeah. Well, there's a square though before, right? 2x1 and squared is the part squared. Make sense? Okay. All right, so the arc length integrals can be really tricky because you have to have the perfect square root type of setup.
We'll take a 15-minute break.
We already took a break. There's only 10 minutes left in class. No, you can't take a 15-minute break. Now I get lost my train of thought. So we're going to the next type of integral is called a surface area integral. And what it does is take an arc length integral and it multiplies the square root by something in front. And so what happens with the arc length integrals that are sometimes super complicated, they become easier because we have a function out in front of the square root which will allow us to use substitution. So that's typically what's going to happen. So let's take a look. So we're going to go back into 3 dimensions. Back into 3 dimensions here. If we take this, and we're only going to look at surfaces that are very symmetric. They're going to be found by doing rotations. So if we take that curve and we rotate that around the x-axis, we're going to get this this surface. Not a solid, it's a surface. So it's paper thin. Well, just like with the other objects that we looked at, we want to take slices and we want to figure out a geometric shape that represents that slice in a reasonable way. So we've had all sorts of different options. In this case, when we do these slices and we take very thin slices, the representative geometric object is going to be the base of a cone. So we call that a frustum. And so we can sort of think of a surface of revolution as being a bunch of frustums that are glued together. And the frustum is going to have, the approximation part is right here on the slant height. But as those frustums get narrower and narrower, that slant height approximates the bend of the curve better and better. So frustum, we're going to do all the stuff we did before with the ds. ds is going to be 1 plus y prime squared, square rooted times dx. Now, this is a formula that you may not know yet, but you should know it soon. The area of a very small frustum is going to be 2 pi r ds. 2 pi r is the circumference, 2 pi r, and ds is going to act like that tiny slant height. It's that slant height that's going to be approximating the bend in the curve. So that little bend in the curve, wherever you're looking, that slant height is ds, and that's going to approximate it. So ds is a little piece of slant. That is our integral, 2 pi r ds. Once again, we don't know anything about s. If we knew something about s, then we could just integrate with respect to s. But we don't know anything about s. So we take the ds, we don't know anything about s, and we do what we did with arc length. We replace ds with its equivalent form with a dx or a dy, depending on which direction you're integrating. And notice that the r, the 2 pi r, the function is going to give us the radius. Just like it did in other problems that we looked at with disks and washers and shells. So here is our formula. It's the ds formula with one change. There's a 2 pi r in front. So 2 pi r is the circumference of the circle, and then ds is our arc length integral, which puts the square root of that into it. So that is how we are going to find the area of a surface. So let's try one. So here we've got a little piece of curve. It's coming from the function 8 root x, where x is going from 9 to 20. There's a picture of it. We're going to rotate it around the x-axis. So we're going to create this bowl type thing that's hollowed out, or whatever we want to call it. It's like a, whatever that is, a tube of some sort. All right. Once again, we know we need the derivative. So with arc length or with surface area, we need to plug into that 1 plus y prime squared. So we need to take a derivative. So the derivative here, that's x to the half. Half comes down, multiplies to the 8, giving a 4. And then we subtract 1 from the exponent, and we get negative 1/2. So there's the derivative. We know that we need to square the derivative to put it in the arc length formula. So that's going to end up being 16 divided by x. 4 squared is 16. Square root of x squared is x, but it's got a minus sign, so it's in the bottom. So there is our derivative squared. So now the arc length, the surface area, capital S, we're going to integrate from 9 to 20. So out in front, we have 2 times pi times r, 2 pi r. And if we look at our picture, what's r? The function, 8 root x. All right, r is measuring from the x-axis up to the curve. R is measuring that. Well, that's what the function measures. That's the job of the function. It tells you how far you are from the x-axis. So it's going to be 2 pi times the function, 8 root x. Now we have the ds piece, which we just spent a whole chapter doing. That's going to be 1 plus the derivative squared. So that is what our setup looks like. And then a dx. Okay. That's a pretty nasty looking integrand. Hopefully it gets better fast. Constants all to the front. So it looks like we're going to have a 16 pi out in front. 16 pi. And do you see 2 square roots? And what we know with square roots is that 2 square roots combine into 1 by multiplying the insides together, right? So if we have the square root of a times the square root of b, then that's the square root of a times b. So we can take and turn all that into 1 square root if we take the inside and distribute this inside to that inside. So this is going to become x plus 16. And that is integrable. So these surface area formulas often turn out nicer than the arc length formulas because the function out in front is going to often help us to either integrate with substitution or maybe just combine and simplify. So this, again, you can use substitution if you want, but it's easier just to use the whole reverse chain rule idea, even though the reverse chain rule here is just 1. Right? The derivative of x plus 16 is 1. So we're going to say, okay, x plus 16 to the what power? So it's to the 1/2 right here. Then we add 1, so we get 3 halves. And then we divide by 3 halves, so we multiply by 2/3. And then we have to divide by the derivative of the inside here, but the derivative is 1, so we don't have to do anything. So if this was a 5x plus 16, we'd divide by 5. But it's not, so we don't. So we go 9 to 20. And we're going to have 32 pi divided by 3 multiplied by, let's see. Plug in the 20 first. 20 plus 16 is 36. The square root of 36 is 6. 6 cubed is 216. Minus. Plug in the 9. 9 plus 16 is 25. Square root of 25 is 5. 5 cubed is 125. So we'll get that. And then whatever that subtracts to, not that. And then multiply that. That's not divisible by 3, so multiply that out and you got it. So the surface area ones can be a little bit easier actually than arc length, even though the formula looks more complicated because you have the 2 pi r up in front. But that 2 pi r is going to make the integral easier in most cases. All right, we have time to do one more. So unless someone has a question. If someone has a question, let's get it. Any part of the ds that doesn't make sense? So ds is always square root 1 plus y prime squared. Let's try one more. So here's the formula again. Another piece of arc. It's going to rotate around the x-axis and create this thing. That nice surface. Very nice surface. We always need the derivative. In calculus, if you have no idea where to start, take the derivative. The derivative is almost always important. So the derivative here, we bring the half down. So we have 1/2 the quantity 4x plus 6 to the negative 1/2 multiplied by the derivative of the inside. So we multiply by 4. So there's our derivative. Then we have to square. So when we square it, let's combine the 4 and the half. So that's going to be a 2. 2 squared is 4. And then we're going to square that other piece, poltergeist. And when we square that other piece, this becomes 1 over 4x plus 6. We could cancel out a 2. There's 2 common to all 3 terms. So we could get that. All right. So now let's put it into the surface area formula. So surface area, capital S, is going to be the integral from 0 to 5 in this case. When we look at our picture, there's the radius. The radius is measuring from there to there, which is what the function does. So we're going to have circumference 2 pi r. So that part's the 2 pi r, multiplied by ds. ds is the square root of 1 plus the derivative squared. We're going to have this. Have that. Once again, we see 2 square roots. So what do we do to those 2 square roots? Combine them. When you take 2 square roots and you merge them together, you multiply the insides together. And for this particular problem, when we merge those 2 insides, I'm thinking about the 4x plus 6 times 1. 4x plus 6 times 1 is 4x plus 6. And then 4x plus 6 is going to go into this numerator, correct? It's going to go into that numerator. So we're going to have 2 times 4x plus 6 divided by 2x plus 3. And that cancels and gives us eek. That gives us, doesn't it go in twice over there? So 4x plus 6. This is going to go into there 2 times. 2 times this denominator matches that, and then 2 times 2 is 4. So we're going to have that. So we're going to end up with 2 pi integral 0 to 5 square root of 4x plus 10. Reverse chain rule, add 1 to the exponent. So that exponent's a half. We add 1 to a half, we get 3 halves. Divide by 3 halves means multiply by 2/3. And then reverse chain rule says divide by 4. And then we plug in the 5, plug in the 0, take the difference, which I'll do, but we can stop now. I'll write it down now. Do some math this weekend. Do some math this weekend.
Well, it's not 2/3.
Yeah.
Is that the numerator, or is that 2/3 of 5 seconds?
2/3 times the next fraction. Yep. 2/3 times the next fraction. You out here? Can't take any more for now? All right, have a good one. Good to see you. Enjoy your weekend. Let's see, let me pause the recording. What were you guys doing in Cal 3 today?
Just starting to dip my toe in.